This is ST300 Week 8. Welcome back, everyone. And now we're looking at part 2 of the GLM theory. This week's lecture is going to be shorter, on the short side, but you can rest assured, guys, it's got all the content you need. Recap. So what did we do last week? We presented the GLM model. And we started to look at parameter estimation. As a recap, remember, we can't use OLS because the GLM models, they are nonlinear in the parameters. And instead, we started to look at the MLE. And we derived the Newton-Raphson and the Fisher scoring. And then we left off there by saying that Fisher scoring can be implemented as a weighted least squares. And that's what we're going to do first of all today. And then we turn attention to hypothesis testing. And then just a quick mention really about residuals and diagnostics. We're not in this course really going to go into that, into the practical side of stuff. So we don't really need to discuss that much. Okay. So the first slide is the iterative weighted least squares, or otherwise known as iterative reweighted least squares. We showed last time that the score vector can be written like such a thing. And if the canonical link is used, the canonical link I've written here in the pink here, if that is used, the score can be rewritten as the following. And this in some form can be written in matrix form, which is useful for coding or computing side. And you can interpret this as the sum of the input vectors. This is the X transpose, weighted by the error. So that's the difference between Y and mu. So the closer is a component of the score to 0. Hopefully that means the difference between these two are very small. That's pretty good. That's what we want. And the corresponding Hessian for 1 is, all right, again, this is using canonical link, which you can write in matrix notation. Now W here is a diagonal matrix. So that is one that is a square matrix with off diagonals equal to 0, but the on diagonals, they're equal to, in this case, these guys. Now, in case you're wondering how I go from the sum notation to the matrix here notation, I'm using the following result on this slide. So here we've got the sum, and here we have matrix notation. So this is from matrix to matrix multiplication. Now let's kind of discuss how we reach this IWLS. So using the Fisher scoring updates, we can write, which we showed is this expression. Now, if we substitute previous results based on the score and the Hessian, so therefore we can get the information into here. Right, so the blue here is, you can see color coded it, that's that. Okay, so that's self-explanatory. And now what I've done here, you can see the next line here is, let's call this A inverse this A. You can see that's the same as that. So then it's A inverse times that. Well, that's this guy here. So that's fine. And then what I do is this bit in gray here, that I bring down, that is now yellow. And everything else, I introduce a new notation, is Z. And this is Z is called the working response. Now look at the form of this and think back to weighted least squares. So looking from the slides, week 4 slides, look at the weighted least squares. So you can see the same structure, right? So W here are the weights. Instead of Y, we have this working response. Remember, like the response variable is another word for the Y variable. And so that means that we can involve using the updating equations, we can run it like weighted least squares. So how do we set it up? We'll initialize your parameters. And if we're using the canonical link, it doesn't really, we don't have to worry too much about how we initialize it because we'll know that from wherever we start, we're going to reach the global optimum. Right, set K to 0. Then next step, obtain the working response and the weights. Now these things with subscript K in the parentheses, these are dependent on the current parameter beta at that kth step. All right, then we regress the working residuals on X with the weight W, like such and so, and to obtain the updated weights. So everything on the right hand side here is computed at the current weights. X does not depend on the beta, everything else does. And then you have some updated parameter beta, which then you feed in now, then that will become in the next round, it will become the current beta, and then you iterate till some stopping criteria is met until you have reached convergence. And if you're using canonical links, you know that it's a convex optimization problem. You will reach convergence. But do you always reach convergence? Well, not if the problem is not a convex one. Not necessarily. All right, so under regularity conditions, which are met by the GLM, so MLE is asymptotically normal, right? This is a result you've seen like from ST300 or 206. And we showed that the inverse of the information is this guy here. Now, this does involve the dispersion parameter phi. And just to say that although that phi is not required for estimating beta, it is needed for the inferences where the covariance matrix is required, such as when we're doing hypothesis testing. Having said that some GLMs, the phi is known. For example, in the binomial and the Poisson distributions, this phi is 1. Obviously, implicit in my statement there, the binomial and Poisson distribution belong to the one-parameter exponential family. Now, how about if phi is unknown? So some cases, for some members of the family, they are unknown. Well, we can estimate it by MLE, but it's more common to estimate it by method of moments. And using this equality, it suggests the method of moments estimator, which I'll leave for you to figure that out. And so then for the estimated covariance matrix, asymptotic covariance matrix, we would just replace the phi by the estimated, the phi by the estimated value. Yeah. And where the W here, they're computed from the last iteration of the IWLS. And IWLS, that's how R estimates the GLM using the GLM function. Okay, now at this point, it's just a natural point for a break, because after the break, we'll look at hypothesis testing. Okay, so back to hypothesis testing now. So the MLE-based tests, such as the WALD and the LR likelihood ratio test, are the ones we're looking at today. Now, the material on the WALD test is pretty similar to treatment to the first part of the course. So you see very close similarities. So we're testing the linear restriction here. with k number of restrictions, then the wall statistic is, I'm just stressing here that this is an asymptotic test based on large sample theory here. This is statistic is tends in distribution to the chi-square, where degree of freedom number equals the number of restrictions. And the argument to reach this, that is the same as what we saw for the linear model. And here, down here, I show you kind of, just remind you. All right, so an example. What is the asymptotic distribution of this constant matrix of constant, sorry, times beta hat, where beta hat is obtained by IWS for a certain GLM? Well, okay, there's your answer. I don't need to explain this because this is from part 1 of the course and also in exercise 4. Now the next part, so we want to test the linear restriction here. Now this is in matrix form, so there's two things here. Beta 1 plus beta 3 equals 1 here. That's one restriction, one thing, and we also have beta 2 equals to 0, right? So the joint test of these two equalities against that, it doesn't hold. So what do we want to do? We want to write down the null hypothesis in the form, okay, linear restriction, obtain expression for the wall test, state the distribution under the null, right? And the final answer should be not contain matrices or vectors. Okay. All right, so you can see something I did earlier right here. So I've written out the restrictions. This is the first one. This guy equals to 1, second one like that. So why have I purposefully written it like this? Because that make it quite clear to see that how it breaks down into A times beta equals V0. So the way I would write this out first is like I did in part 1 of the course, or maybe I write down the restrictions first, 1 and 0, just simply mark that into a vector, okay, like that. And then the beta, now the beta in the question, it's counting from subscript to 1, not to 0, right? So just know that's why it's 1, 2, 3 like that. So vector of the parameters, and then A, I'm just going to write out the end 1, 0, 1, 0, 0, 1, like that, okay? And when you get confident of doing this, you can just miss this step here. I could go straight to stating what the A is. Now, we'll also be needing, for the walled test, we'll need the information, or the inverse of the information. Now, given an information matrix here, we've got to inverse it, right? Being 3 by 3, you might be thinking, oh, you need to do Gaussian elimination or something like that, but you don't. Because this one here, as I kind of drawn out here, is what we call a block matrix. So block matrix here is where you've got like square elements. So here, it's a 1 by 1. This is a 2 by 2, right? Of non-zero terms. Stuff off the blocks are all zeros, and they don't have to be, they can be vectors. They don't have to be matrices. So this is here is what we call a block diagonal matrix. And to find the inverse of a block diagonal matrix, you just simply find the inverse of each of the blocks. So this is 3, that's going to be 1 over 3. Now this guy here is a 2 by 2, and you can use a standard way to solve a 2 by 2. Okay, so no need for Gaussian elimination, although you're welcome to use it, but take a bit more time. All right, so then to write out the walled test, so under the null, a beta hat tends in distribution to normal A would mean A beta, and the covariance matrix, this guy, right? From part 1 of the course, you saw that. And the walled statistic, now you don't have to derive, well, you can see from here, you can read from this line that this is true. But if you want to kind of do a semi-proof or proof, because you don't want to memorize this result, that's fine. But you don't really have to memorize it, because you can get, once you get confident, you can just see it's from this line. Okay. Anyway, it doesn't harm if you have to do a semi-proof to get to this from here. Then I make the substitution. Okay, this is all clear now. I take the inverse of this guy. Right, you can double check whether I got that right. So the inverse of this guy is that. Question says, now don't leave it like this, because the question says, express your answer so it doesn't involve matrices and vectors, right? It does not contain vectors or matrices. So we multiply out. We're multiplying out, we've got scalar now. And this wall test is tends in distribution to chi-square, degree of freedom equal to the number of restrictions, of which there are 2. Okay, the restrictions are given by the number of rows of A here, 2. One final comment is don't need to go further than you do not here need to expand out the square, like some of you, a small number of you did for the exercise 4, which was a similar question to this. Because there's only a point in expanding the square if you get something which is a simpler form or something which is more interpretable, maybe a geometric object. Yeah, here it isn't. So leave it as it is. Right, next, turn attention to the likelihood ratio test, which can be used to compare nested models. Now, here we introduce 2 benchmark models. Benchmark are basically just these are models in itself are not too useful other than for you to compare your model to your fitted model. So we have the null model. The null model just assumes a common mean for all the observation, your n components. And an illustration of that, suppose that the y is from a Pearson. So the ith component is Pearson, and instead of have a parameter lambda I, it's just lambda, yeah, because that is the null model assumes it is has a common parameters. And in this model, it does not depend, your parameter is lambda, it does not depend on covariates and therefore does not depend on beta. Your null model is basically your kind of, when you first did MLE in ST102, they were null models, okay? They're null models. Now the saturated model also does not depend on the covariates and so does not depend on beta. This is a model where it has the same number of parameters as the observation. So basically the parameters are going to be equal to the observations. Now, why are these guys not useful other than comparing your model? The null model, because, well, both of them do not depend on covariates, so how can they be useful? Well, the null model is too simple, does not depend on X, we've said that there. A saturated model does not depend on X, but it gives the best fit. But other than that, it can't do like explain relationships between X and Y's or make predictions on new data. Now, to assess the goodness of fit, here we introduced like a new terminology for this course. It's called the scale deviance. And we want to differentiate this to the deviance, which has been used in the course to date. And there is a slight difference, but quite important one. So the scale deviance will define like so. So it's like twice the difference of the log likelihoods, where the log likelihoods is evaluated at for the saturated model to the model, your proposed model. So your model will involve covariates, so therefore it will have betas. So that's what this is denoting. In previous years, this whole thing was called deviance, yeah? We're calling it scaled deviance. And what we're calling deviance is just phi times this. So observation is that scale deviance is the same as deviance if phi is 1, which it is for common, some of the common members of the 1-parameter exponential family. So one reason why I want to kind of make this differentiation is because then it can be seen that the deviance generalizes the residual sum of squares for the linear model. So the deviance will be equal to the RSS of the linear model if you have a linear model. And the second point to note is that this deviance is what R calls a residual deviance. All right, so show you that second point, that the RSS is equal to the deviance. In the case of a linear model. So up here, I'm fitting some linear models. So that gives me an RSS of, okay, this figure here. Then over here, I'm running the same model, but this time by the GLM. So as a GLM, and the family here is set to Gaussian, so the error is following Gaussian or normal. And then we look over here, under here, the output. You can see where it says residual deviance. This number is the same as that. Hence, for the linear model, the residual deviance is equal to RSS, which is stated in this line. So the scale deviance compares the fit of your proposed model through the log likelihood to a perfect model. Now, as the likelihood evaluated for your proposed model, that will be less than or equal to, so it can't be bigger than the log likelihood for the saturated model, so therefore scale deviance can't be negative. And under some conditions, okay, to be discussed for individual GLMs, then the residual, this scaled deviance, we can use it to test the goodness of fit, where the null hypothesis is the proposed model is adequate fit relative to the saturated model. Now, what is the idea here? The idea here is, since that it's a difference between the log likelihoods, if your model is pretty good, then the value, then your likelihood value computed for your model should be quite close to the saturated model. If it's like 1,000,000 miles away, then it's basically saying it's not really a good fit. Okay, so therefore large values of your D star will indicate that you don't really have a model that fits well. And so why might it not fit well? It might not fit well because of the choice of link function that you have is not suitable, or that the linear predictor that could be improved upon, or such as, for example, you might have omitted some relevant covariates, or the functional form you haven't got right for the X variables, and so on. Okay, so on this slide, just comparing the null deviance. So we have, on the one hand, the worst possible fit. This is the fit which is on just a model which contains an intercept. It does not contain any covariates. That is going to give us the worst fit. And then at the other end of the spectrum, we have the perfect fit. So this will be for the saturated model. And the difference in these two here, we call the null deviance if we compute the deviance comparing the null model to the saturated model. In other words, the null deviance is if we replace this guy here, our proposed model, by the log likelihood for the null model. Oh, which I've stated right here. And so we'll be somewhere in between these two. We might be over here, and then this is we're comparing our model to a fitted model, and that is the deviance. Remember, if our model is pretty good, this difference should be pretty small. Small enough anyway not to reject the null. So where can we find these on the output? Well, if we're running a GLM in R, we use this function GLM. And just to point out, the moment is that what we have here is the null deviance and residual deviance values. okay? And the dispersion parameter in this case for this particular model, which we'll talk about next lecture, is a family binomial. It's a logistic model for some of those of you who already know about this logistic regression. The dispersion parameter is 1. So what does that mean? It means that the scaled deviance is the same as the deviance. So yeah. All right. An alternative measure for the goodness of fit is the Pearson's chi-square statistic. Now, this bears a relation to what was taught in ST102 when you looked at the goodness at chi-square for the goodness of fit. This expression here. So you can go back to that in the notes mentioned here. And asymptotically, though, in large samples, they are pretty much asymptotically the same. So that's the only thing to note. All right, example time. In this case, we have the response here following exponential with a parameter lambda, and this does belong in the exponential family density. And a couple of things to note here is that in part C, it says use minus log lambda I to be the link function. In other words, I've written here in black, that's what it means to say it's the link function. I'm going to do part F, which is to derive the deviance. So for the deviance, we need to compute the log likelihood for the saturated model, and then we need the log likelihood for our proposed model. So for the saturated model, the I component for the log likelihood is, okay, simply for the I component. Now put to lambda also subscript I, because remember for the saturated model, each parameter can be different and does not depend on your covariates. So it also does not depend on, therefore, the betas. All right, so this is log likelihood. And so when we differentiate this thing, there's only parameters lambda, there's no betas here. So I'm differentiating this guy with respect to lambda I. Yeah, that's straightforward. And okay, so this is the set this to 0, the score to 0, and rearrange. And so I just put a tilde on this lambda I to denote this is the parameter estimate for lambda for saturated model. And this will be for the ith observation. Okay, so the answer does not involve betas. That can't make sense. So here it involves only the observations. And it cannot involve X, right? So yeah, you've got X or betas, that can't be right. So the log likelihood for the saturated model is, so I go back to the log likelihood here, and that's the ith component. Since the yi's are assumed to be independent for the traditional GLMs, so therefore the log likelihood is a sum of the ith components of the log likelihoods. So it's sum of this guy here, but I replace the lambda I by lambda I tilde, like this. Okay, like that in yellow. And okay, you can leave it like that. I'm going to just rearrange this so I don't have this fraction over here. Right, so there, I'll call this equation 1. Also, we can show, and from the part 1 of this question, part A, you'll have shown that the dispersion parameter is 1. So the D here, as for the deviance, so the deviance is, write this out, I'm going to call this 2. And then the likelihood for our model, beta hat, now this does involve obviously the covariates here, Okay, so using the fact that we have the link function, we were told that in part C, that's why I was saying this. So where we see minus log phi I, I'm going to set that to that. Yep. And so that's what I'm doing right here. And to get this, and to get this, okay, where I saw this guy here and this guy here. And then I just say I'm going to substitute 1 and 3 into 2, and we'll leave it at that. Now you can actually do the substitution, and that would be useful if you can cancel terms in 1 and 3 or gather to make it simplify it. But here I cannot see anything simplifying, so I'm just going to say this. Before we leave this, note that since phi is 1, this deviance is the same as the scale deviance. Also, note carefully, guys, the question here is asking us to derive the deviance, which is a different thing to deriving the null deviance. Okay. The null deviance would be comparing the saturated with the null model. All right, second example for a binomial where the yi's come from some kind of binomial distribution. Okay, log likelihood should be straightforward. The saturated model, again, we'll just pick ith component here, and then this will be a pi I, not a vector, but just a scalar pi I, and do the usual thing, differentiate with respect to the pi I, set to 0, solve, and then you can see, and this kind of makes sense, intuitive sense. This for saturated model, this proportion, this probability of proportion is the sample proportion for the ith group. Yep, and which depends only on the data, does not depend on x, does not depend on beta, because it doesn't make sense to do so for saturated model. And so we substitute this beta I tilde, where we see the beta, sorry, what am I saying beta? Pi I tilde, where we see the pi tilde up here for this sample proportion, right, which I've done in blue here. All right, so that is the log likelihood for saturated, but also then since it's asking for scale deviance, okay, scale deviance, so we also need it for our model. So our model here will depend on covariates, and let's say we've got p number of them, and they will, and the pi and the probability here will be some model of will depend on the covariates and hence on beta. And so I'm going to put a hat on there to denote that it will be the one which is estimated by MLE. And remember, again, this will be some function of beta. And so where I see the pi now, I'm going to replace it by pi hat, right? And this will got beta here. So yeah, instead of saturated now, we've got for the model, we replace that, I've got beta hat here. So we've got these. We've got these pi hats, which are functions of beta. So the scale deviance is, right, so write this and just make a substitution in this case. Now, why I'm writing it like this in terms of, instead of pi I here, writing in terms of observations is, well, because you guys know the relationship between the observed counts and proportions for binomial. Okay, so that's the case where you want to compare your model to the extreme model, and that's goodness of fit. But also we can like compare nested models. So we have like model 1, say it's nested in model 2. Now, if this model 1 is true, I mean, if the small model is true, okay, some sense true, we have the likelihood ratio statistic defined this way. It's a difference of the scaled deviance. And if you substitute for the definition of the scale deviance, you'll see that the likelihood evaluator, the saturated model, cancel. So hence you only got now 2 times the difference between the log likelihood of the bigger model minus the one from the smaller model. Okay, so therefore this difference is non-negative. If it's negative, you've got them the wrong way around, the definition. tends in distribution to the chi-square, where degree of freedom is the difference in the number of parameters between the two models. Right, so I've written a note here in yellow here, which is like this asymptotic distribution for this difference in deviances is more accurate than the approximation for the distribution of the scale deviance. This is because notice that the degree of freedom between the two models, P2 minus P1 here, is fixed. It's not a function of n. So it's a case of where the parameters is fixed, but n goes up. That is the usual asymptotic setup. Worth going back to this slide just to point out to you. That's why I highlighted this for the goodness of fit. That's under some conditions, right, to be discussed. Because in this case, your degree of freedom n minus p is growing with n. So the parameter here is also changing with n. So it's not as straightforward as this case here. All right, so the goodness, comparing the nested models there, the null hypothesis that a smaller model is enough, well, is adequate relative to the bigger model. And yeah, you guys know what to do, usual one-tail test. But up to now, that assumption, the condition required for either of those tests is that phi is known, right? It turns out phi is 1, as I said, for a number of these common members, popular members of the exponential family. But what about if phi is unknown? And it will be unknown for the following members of the family, the gamma, inverse gamma, Gaussian GLMs. Well, in this case, we can't use for testing nested models, we can't use the change in the scale deviance. But instead, what we can do is compare the nested models by an F-test, as we did in first part of the course, which you can see the notes here. I'm just showing you so you can compare. So difference in residual deviance, difference in number of parameters. In other words, it's like number of restrictions divided by some estimate here of the phi, where phi is estimated from the larger model, like this, say. Then you can see like, okay, these guys involve phi, but up down here, they involve phi, the phi cancels out. And that's another way to write it. But if you think like that, where the phi's cancel out up here and this one here, then recall we said that for a linear model, the RSS is the same as the deviance. Then that means we'll have a difference of deviances here, the deviance there. And if you look at that, it's the same thing, isn't it? Yeah. In the case of a linear model. Okay, so that's testing. Now, how about R squared? Because that's something popular that we look at. Although remember, we tend to misuse for linear models. Well, we can't use the usual definition of R squared because, as in linear models. Why? Because in linear models, that R squared is based on the RSS, right? That's the loss function there. But for GLMs, we don't use RSS, we use MLE. So we need some kind of adjustment there. And there are a number of these adjusted R squared, well, wrong word there, pseudo R squareds, okay? Like, it's like having R squared features, or can be used like R squared. One here called McFadden's R squared, formulated in terms of the deviance as, okay, so it's 1 minus the ratio, a fraction of D1, which is the deviance of your proposed model, divided by D2, D0, which is the deviance of the null model. It could be shown that this R squared is bounded, it's between 0 to 1. The interpretation of this R squared, though, is different for LM, for the linear model. Now, notice that this deviance for the null model is fixed, yeah? It's not model dependent, whereas D1 will change depending as you change your model. So think about it. If your model fits the data much better than the null model, then this ratio, it won't be big, it will be small. Yeah, so think why? Why is it small, not big? Just go back to the definition of what a deviance is. All right, and then so the pseudo R square will be relatively high. All right. Okay, and that brings us pretty much on to the last thing, which is really just touching on residuals and diagnostics. It's not really an important part of this course, but I just wanted you to know. It's basically just something you know, I want you to know that exists, right? So standard diagnostics of linear models can be extended in some way for the GLMs, okay, all these diagnostics that we've seen for the linear model. Now for the residuals though, there are a number of residuals for the GLM. I'm going to focus on this deviance one. So deviance residual is one defined such that the ith component of it, when you square it and sum it, that will take equal to the deviance. Okay, equal to the deviance statistic. And the sign of di takes the same sign as the difference between yi and the fitted mean. So this one is a popular one. Another popular one is based on the Pearson. All right, so it's based on Pearson. If you hear about that, that's it. And it's similar kind of. Half one here is if you square the Pearson residual, square it, sum it, it will equal to the Pearson goodness of fit statistic that we saw earlier. All right, and the working residual, okay, this is based on IWLS algorithm. Okay, it's defined this way. It's like this, remember, was the fitted response, and this is the fitted value based on the kth iterate. And this is called the response residual, and it's the least useful. So anyway, just know it exists. And that's about it, really. Okay, so quick summary. I know the lecture has been on the shorter side, but as I said, the content is all there. Not missed anything out for you guys. So we've looked at, now completed the MLE. So now you know all you need to know about parameter estimation with MLE for the GLM. And you know how we can introduce the idea of this weighted least squares into updating the parameter estimates for Fisher, right? And maybe I didn't say, like, when you do Fisher, you need to obtain the Hessian and the information matrix, obviously, yeah. And that involves like not just first derivatives, but second derivatives, all right? And which can be challenging when you've got massive data sets. And so if you use it as a run it as a weighted least squares, that's very convenient. And this is how R does it. All right, so week 8 class, we'll go over the exercise again, theory exercises from 4, and if I have time, look at 7. And then the rest of the time, you can get working on exercise 8 which is on this topic, because on this material, this lecture, because it's a bit more challenging, students find. All right, guys, so thanks for watching, and I'll see you in class.